Renko was previously working at Boeing, and he got his degree from Brown University. And he will tell us about how to simplify dense models with 3D buildings while still preserving legibility.
Thanks, Emil. Thank you guys for coming here. It's a great privilege to be at Google. So I'm here today to talk about kind of a broader research question that I've been working on. And the idea is try to understanding urban environments through the use of a thing called urban legibility. And I'll talk about that in a little bit. So this talk is actually going to get broken down into about 2 parts. The first half is going to be on simplification of the urban models while maintaining urban legibility. And this is a talk that I gave at SIGGRAPH this summer. So I apologize to people that were there. It'll be a repeat, almost verbatim repeat. And the second half will be on discussion and future work, where I'll be talking about some of the things that we've been working on, as well as some of the things that we would like to be working on in the future. And before I start, I just like to talk a little bit about what we're doing at the Visualization Center at Charlotte. And specifically, one thing that we've been really interested in is in this idea of knowledge visualization. And to give you an example of what we mean by knowledge visualization, you can imagine like you have a screen of labels, there's lots of text, and they're kind of overlapping each other. Now, if somehow you can take the screen and extract some sort of higher knowledge, either from the scene or from the user, then it is theoretically possible that you can focus your resources on the things that you want the user to focus on. So in other words, we think of it as you want to minimize the resources that you're using, but you want to maximize the information that you're giving to the user. And resources can really be anything. I mean, it can be CPU time, it could be a number of polygons, and in this particular case, it really is just the number of pixels that you're using on the screen. To give you an idea of what we consider as a great knowledge visualization paper, here's something done by Agrawala and Stolt, who are both at Stanford. They're with the Pat Hanrahan's group. And this paper is on rendering effective route maps. And here's an example of directions that would be given by MapQuest. And you see that this direction is physically accurate. It shows you exactly how to get from point A to point B. But that's about all it is. You don't really get a lot of information out of this. Whereas, typically speaking, if you ask somebody to give you directions, this will be something that people would draw you. So this hint sketch thing is not at all physically accurate. I mean, it's shortened the Highway 101 into a very small amount, where if emphasis more on how you get onto Highway 101 or 110 and how to get off. So of course, in their paper that was published at SIGGRAPH 2001, they were able to mimic what humans typically do, and in this case, really showing off the important information in this task of giving people directions and maps. So we want to take this idea of knowledge visualization and apply it to urban models. So here's a model of a city in China. And the question is, what is the knowledge in this scene? What is it that we want to be able to preserve and to highlight? To answer that, we turn to this idea of urban legibility. And urban legibility is a term that was made famous by Kevin Lynch in his 1960 book called The Image of the City. So what he did for this book was that he went around the city of Boston, and he just asked local residents and asked them to sketch out, just kind of use a pen and sketch out their immediate surroundings. So what he actually got was a stack of these images that you see on the right here, where people just simply sketched out, this is where I live, this is a big road around me, and so on. And he took this stack of sketched images, and he categorized the important things into 5 groups. He categorized into paths, which are highways, railroads, roads, canals; edges, shorelines or boundaries; districts, industrial, residential district; nodes, which you can think of as areas where lots of activities converge. So as an example, it's Times Square in New York City. And then landmarks. And landmarks can really be anything. It can be a tree, it can be a post sign, it can be a big building. It's whatever people use to navigate themselves in an urban environment. So Kevin Lynch defined this idea of urban legibility as the ease with which a city's parts may be recognized and can be organized into a coherent pattern. So that's kind of a mouthful, but to me, what that really says is, if you can somehow deconstruct a city into these urban legibility elements, we can still be able to organize a city in that coherent pattern. The use of urban legibility in computer science really goes back a little ways. Ruth Dalton, in her 2002 paper, just chronicles the history of what people have done in computer science in the use of urban legibility. And it kind of broke down to two groups. There's one group that tries to justify whether or not the idea of urban legibility actually makes sense. So what they did was they tried to figure out if these elements are actually important to human navigation. And what they found out, interesting enough, is that paths, edges, and districts are very important to navigation, but landmarks are kind of questionable. There's some groups that think that it's very useful. There's some groups that say that it's totally useless. And the one element that's missing here is the element of nodes. And people have not really been able to successfully quantify what really a node is. So there hasn't been as much research done on trying to figure out if nodes are helpful at all. And the other group of researchers just use urban legibility, and in particular in graphics and visualization. Most notably, Ingram and Benford has a whole series of papers where they try to use urban legibility in navigating abstract data spaces. So the question is, why do we decide to use urban legibility? And to give you an idea, here we take an original model. These are a bunch of buildings in our Atlanta data set looked at from a top-down view. This is what you would get if you use a traditional simplification method such as QSlim. And I'm assuming people know what QSlim is. But what you see is that a lot of the buildings get decimated to a point where it doesn't really look like a building anymore. Whereas our approach is a little bit different. We take an aggregated approach, and this is what you would get. And if we apply a texture map onto our model, this is what you end up at the end. So it's actually really interesting that when we take these four models and we put in the fly-through scene, just kind of a test scenario, and we measure how many pixels are different from the original model, and this is the graph that we get. So you don't have to look at it carefully, but the important thing here that I'm picking out is that basically using all these models, they end up with very, very similar differences in terms of pixel errors. And what that says to us is that even though you look at these four models and you say, well, they look very different to me, but in effect, if you measure it purely quantitatively using pixel errors, they actually come out to be very similar. So what that really says to us is we can't really just use pixel errors as the driving force behind simplification of urban models. We have to use something a little bit different. We have to use a higher level information in here. And to simplify this, let me just state our goal for this project is to create simplified urban models that retain the image of the city from any view angles and distances. And as an example of what we get, you see the original model on the left. The middle image shows the model having been reduced to 45% of the polygons, and the last one is 18%. And you kind of see a little bit of a dimming effect across when it goes from original to less polygons. But the important thing here to note is that when you're doing this, the important features in the city are retained. So for example, the road here is still kept. The city square area is kept. And you pretty much still get the sense that this is the same city that you're looking at, even though there's only 18% of the polygons in the scene. Right. And I'm just going to run the application really quickly, and hopefully nothing goes wrong. Let's see. OK. So this is using the Chinese city data set, and this is running live. So as you can see, I can just kind of look around, move to different places. And here, hold on one second. This is where a demo goes wrong. OK. So I'm just going to start zooming out from this view.
Can you mention how you got the geometry and the texture?
Is
that made up texture?
These textures are totally fake.
And how about the geometry?
The geometry is actually real. So what we got was we got the original footprint information, and we got approximate height information in terms of number of stories or number of flights per building. And we estimated that each story is about 3 meters. So the geometry it's kind of the extrusion of footprints. So it's not real in terms of the true 3D models. But the footprints and the positions are actually absolutely correct.
Do you leverage the fact that to make your graphics fast, you get repeated texture patterns?
There's definitely some. but I'll talk about that in a little bit. Yes, sir?
What specifications are you running this on?
Sorry?
What kind of specification machine are you running this on?
As it turns out, I'll get into that a little bit later too. This is.
Could you repeat all the questions?
Oh, okay, sorry. So the question was, what is it? What kind of hardware I'm running this on? And the honest truth is, I have no idea. But what I do know is that this is kind of state-of-the-art laptop from Dell. But as it turns out, I'll explain this in a little bit. But the bottleneck's actually not in the graphics card. It's actually in my crappy code where I'm not transferring data fast enough. It's the pipeline that's actually the bottleneck right now. But that's just my fault. I wrote some crappy code. So here I'm just zooming out from that particular viewpoint, and to demonstrate my point, we're just gonna keep zooming out and keep zooming out, keep zooming out. And at this point, I'm gonna freeze the level of detail simulation. I'm taking away the ground plane. I'm taking away the textures. And when I zoom back in, you see that this is actually what was rendered when you're that far away. And you can see the number of polygons at the bottom right here in terms of how many polygons was actually seen when you're really that far away. So the important thing here to note is that even though we are doing some pretty drastic simplification, we still try to retain the important features in the city. And just to give another quick example of this, I'm just going to run this without the texture. We also take into consideration of height preservation. So what that means is, so I can be looking at a city from kind of an oblique view. And again, if I freeze this process and I zoom out, you see that there's a lot more detail in and around where the viewpoint is. And as you go out further, the models are a lot greatly simplified. But the interesting here to note is, even for objects that are far away, the tall buildings are still rendered separately. So you kind of get that skyline, even when you're looking at from different view angles, even close to the ground plane. Okay. Okay. Cool. Just to give you an idea about what work has been done in terms of urban flythrough or urban walkthrough, and people have tried different things. You know, visibility and occlusion is a popular one, and Peter Wonka has a great paper called Instant Visibility in 2000, and Scheffler has another great paper in 2000 as well in SIGGRAPH. And in here, the idea is that if you use occlusion or visibility, you can reduce the number of polygons that you're rendering, so that you can actually see a bigger scene without actually seeing the bigger scene. And there are people who use imposters or billboards with textures. Started with Marcel and Shirley in '95, and then Cilian in '97 extended it to kind of blend between imposters as well as real geometries. And in '98, Shalabi in his PhD thesis extended Cilian's work, but added in some elements of legibility in there as well. They're procedurally generated buildings. I think this was really started by Peter Wonka in 2003's paper called Instant Architecture. And this year's SIGGRAPH, Pascal Muller has a great paper on procedurally generated buildings. And then lastly, we just have popping like, you know, Google Earth and Microsoft Live. So there are about 5 steps to our algorithm in order to preserve legibility. And in order, the first thing we do is we try to identify and preserve the paths and the edges. And we do that through this hierarchical clustering that I'll be talking about. The second step is in creating logical districts and nodes, and we do that through cluster merging. Then the third step is simplifying the model while trying to preserve paths, edges, districts, and nodes, and that's done through our simplification process. Then we hierarchically apply the appropriate amount of texture, and that's through the texturing process. And these 4 steps combine to become the pre-processing step. And at the end of this pre-processing step, you end up with a hierarchy of meshes as well as a hierarchy of textures. Then we feed all this stuff into the runtime process, where we try to highlight the landmarks and choose the appropriate model to render based on the viewpoint. And that's through the LOD with landmark preservation process. So first I talk about how we do preservation of paths and edges through hierarchical clustering. Here you see the result of 2 clustering methods. The one on the left is more of a traditional thing like k-means and whatnot. And the right is what we use. And you can see that This is cool animation. You can see that the where the two clusters meet in the first example, it doesn't really follow any sort of logical paths. Whereas in our implementation, we really try to make sure that the two clusters are separated on a logical road. And the way we do that is by using something called single link clustering. And it's a pretty simple idea. It basically iteratively groups the two closest clusters together based on, in our situation, Euclidean distance. So as an example, let's say that you have 6 buildings to start with, A, B, C, D, and E, A, B, C, D, E, and F. And you just start grouping them 2 at a time. And eventually, what you get back is a binary tree, or sometimes called a dendrogram. The thing that's interesting here to note is that in this particular scenario, the dendrogram is actually very unbalanced. On one side, you have node A. On the other side, you have B, C, D, and E, and F. And this doesn't work well at all for our purposes. So we had to do a little bit of balancing of the tree by penalizing larger clusters. And the idea here is we want to create a more balanced tree. Here's some sample images of the first few steps of this hierarchical clustering process. And you can see red is one cluster, green is the other. And we just follow one particular path down this process. You can see that throughout the simplification process, the divide between the two clusters mostly follow the road pretty well. Okay. So once we have the clustering, then the next thing to do is to merge the clusters together to create logical districts and nodes. Here's an example of what we mean by creating a logical district. You have one cluster of buildings in red, the other cluster of building in yellow, and the blue outline shows what the merger would be. And this is what it should look like, where the blue outline should just encompass all of them together, including the black space in the middle. So the way we do that is pretty simple. We first find the footprints of each building ordered in a counterclockwise manner. Then you find the 2 shortest edges that will combine these 2 things. Then you just start tracing it, starting with one of the vertices. Now, when we start with the magenta vertex, what we end up with is actually what we're looking for, which is the resulting merged hall. Now, it's interesting to know that when we start with a different vertex, and again, the counterclockwise fashion, what we get back is what we call the negative space, or you can think of it as the error that's introduced by merging these 2 halls together. And this is actually very important because the negative space is what we end up using in determining what model to render later down the process. So once we have that, then the next step is to simplify it. And here's an example of what I mean by simplification. You see on the image on the left is the merged hall of the Atlanta data set. And here you have about 6,000 edges. And the idea here is we want to simplify it without really killing too much of the features of the city. And in this case, we diminish it to about 1,000 edges or so. And I'm just going to show you real quick how this works. Okay. Right. So this is just a small data set that I'm showing. And right now, you see the blue outline. That's the merged hall of all of these buildings together. And as I start sliding these sliders down, I'm actually doing simplification as I speak. So you can start to see that little features are starting to be filled in. And I just keep going, and so what's interesting about this algorithm that we developed is that eventually, if you just keep going at it, you get back the convex hall. So it's not at all the most efficient way of finding convex hall, but you do find the convex hall. Right. So once the polylines have been simplified, or once the merged hall has been simplified, we create what we call cluster meshes. And these are nothing more than protrusion of the footprints, and where we determine the height of this cluster mesh to just be the median height of all the buildings in the cluster. And this is what we mean by what a cluster mesh is. Once we have that, then we apply texture onto all these cluster models. And we do it in a hierarchical fashion. So first of all, we give each cluster mesh 6 different textures. We give it a side texture. We give it a top-down view of the roof texture. And we kind of do an imposter-ish kind of thing where we give 4 roof textures from 4 different angles. And then we put these cluster meshes into bins based on how visually important they are. And the idea here is that if you have a particular cluster mesh that you know won't show up until it's like really far away, then what you can do is you don't have to give it as much texture real estate. So in such a case, what you would do is put it in the earlier bins. And I'll explain that in a little bit. Each of these bins that you see, n over 2, n over 4, n over 8, each bin will contain the same amount of texture resolution. So what that means is, if you have a particular cluster mesh that's put in the first bin, meaning the n over 2 bin, the amount of texture resolution that you will receive will be a lot smaller because there'll be more people competing for it. Whereas further down this pipeline, the more visually important clusters will actually get a lot more texture resolution. So this is a way for us to actually control the texture a little bit, because texture in a lot of these urban models, as you mentioned earlier, is a pretty big problem. So once we're done with all this, then we put this, the resulting cluster meshes and the hierarchy of meshes and the hierarchy of textures into our runtime system, where we try to preserve landmarks and choose the appropriate models to render. So first, we talk about how we choose the right model to render, and we start with the root node of our dendrogram, in this case, A, B, C, D, and E, and F. And then we take the negative space of that particular cluster mesh, and that's shown here as a approximated 3D box that's shown in red. And we project that box onto screen space. And if the number of pixels that occupies exceeds some user-defined tolerance, then what we do is we reject that node and we recursively check for its 2 children. And that just keeps going until you find the appropriate cut in the LOD tree. Next thing I talk about is the landmark preservation process. Here you see the original Skyline on the left. The middle image shows without the landmark preservation, and the last image shows our method with the landmark preservation. And all you really need to do is you add a few buildings that's visually important, and you really give back the sense that the last image is very similar to the original. And the way that's done is basically projecting a user-defined tolerance alpha onto each cluster mesh. And if there's any building in that cluster that's taller than alpha height, then it will be drawn on top of the cluster mesh. In other words, here's a scene of cluster meshes, and you see here on the lower right-hand corner is a little green line, and that's the projected alpha height. And these buildings are drawn separately because these buildings are taller than alpha height, so those will be drawn separately. Now I talk a little bit about the results of what we get out of the system. Here you see this little line, blue line that runs across the bottom of the scene, and that's rendering using the unsimplified meshes, and it's just a constant frame rate. And we see that in this particular case, we have a fly-through scene where the camera starts off really far away, zooms into the model, and flies back out again. So what you end up seeing is when the camera is far away on the top, you have really, really great frame rate. But once you start to really, really zoom in to the point where you're almost touching the ground, then the problem is the overhead of traversing your LOD tree really catches up with you, in which case the frame rate is actually worse than if you just rendered the entire scene independently. And correspondingly, in terms of the number of polygons that's rendered, you see the line on the top, and that's the number of polygons in the static or the unsimplified model. And you see that the two curves are, or the two graphs kind of are inverse of each other because the number of polygons is inversely related to the frame rate. So in conclusion, there are a few things that we found by working on this project. The first one being that when you just use per pixel error, it is actually not at all indicative of the visual quality of your simplified urban models. So what that means is you really have to go towards some higher level knowledge, in our case from city planning, to help extract and retain visually salient features in the model. And in our particular case, using urban legibility, we find that it allows efficient and intuitive simplification of the models. There's some great limitation to what we're doing here. The first one is this rendering engine that I implemented is horrendous. I cut all kinds of corners. So we're not using display list, vertex arrays, any of the newer ideas with graphics card programming. So that needs to be worked on. The second thing is the pre-processing step takes absolutely forever because all the algorithms are basically n-cube processes. We can think of ways to simplify it down a little bit, but it's something that we need to work on. And something that's inherent to this algorithm is that we end up with binary trees as our hierarchy tree. And binary trees are just inherently deeper than quad trees or oct trees. So traversing binary trees just takes longer. And the last thing is we really want to improve upon this by allowing user interactions. And what we mean by that is you can imagine that districts in a logical sense don't always follow roads or geometric distances. For example, if you have a historical residential area downtown, chances are that's not bounded by roads. I mean, that's probably just right immersed into everything else. But to the local residents, that district may be particularly important. So we need to have the kind of interaction where we allow the user to be manually go in there and say, no, this area is a little bit different. This is a historical region, for example. And that pretty much is it. So I want to thank the co-authors on this. Tom, Caroline, Zach, Bill from Charlotte, and my advisor from Brown, Nancy Pollard, who's at Carnegie Mellon at this point. And this project was funded by the Army Muri project and some of the people that I work with in the architecture department. So this is part one. I'll just take some quick questions if you want. The second half, I'll be talking a little bit about what we want to do in the future and all.
So for the questions, please remember that this talk will be available on Google Videos. So reserve all the questions with confidential content for after the talk.
Yes, sir.
So you mentioned that per pixel error is not a good measure of quality.
Right.
How do you measure the quality? How do you decide what's good quality rendering?
You know what? We honestly have no idea. I think. The question was if per pixel is not a good indicator of the visual quality of the simplification, how do we measure our results? And the short answer to that is we have no idea. I think it's interesting, similar to the paper by the Stanford group where we did the efficient route maps. It's kind of the same thing because how do you justify that that kind of direction giving is good? Well, unless you really do a full-blown user study, you won't really know. And I talked to some people about that particular project, and people agree that probably 99.9% of people in the world would believe that that was a good sketch or drawing of directions. However, they mentioned some people living in the islands of the Pacifics that really believe that the Earth rotates around them, in which case chances are that drawing would be absolutely useless to them. So it is very subjective. We thought long and hard about it, and I think at the end of the day, to be able to justify this as useful, you just have to do a user study. Yes, sir.
The slide you displayed how you merge the footprints of two neighboring buildings.
Yes,
that was in a two-dimensional approach. So how do you actually blend the geometry of the two buildings in 3D? How would you deal with the wall not part of the outside there?
So the question is, the cluster merging process is all in 2D. How does that extend to 3D geometry? Short answer for that is it doesn't really extend to 3D geometry. We basically assume that all the buildings are 2.5D. So all you have to do is play in the 2D realm and do protrusion from that. And I'll talk a little bit about future work about the 3D geometries. Yes, sir.
So Facebook was working nicely because you had like flat roofs everywhere. How well does it work with like European style cities?
What's the difference?
Oh well, they don't have flat roofs.
Yeah, okay, right. So the question is how would this work for true 3D models, I guess. Again, the short answer is I don't know, but I'll talk a little bit about what we plan on doing in the follow-up. Yes, sir.
So you mentioned the pre-processing part was O of n cubed.
Yeah.
What's the n?
Sorry, n is the number of buildings. Actually, let me take that back. In some cases, it could be the number of vertices. It's a terrible, algorithm. There's and n cubed is actually the absolute maximum, right? So in reality, it doesn't run at n cubed, but regardless, we never really tested the theoretical limit of where it really is running at. But that's something that we're definitely, thinking long and hard about. Yes, sir.
So, yeah, just to put that in perspective, like how many machine hours did it take to do a few first to do a demo?
For this demo, it's actually pretty quick. In this particular demo, there's about 40,000 models. And that was probably, I would say, half an hour to 45 minutes. But I will be honest with you, when we pushed it up to about 50 to 60,000, I let it run over a weekend and never quite finished. So that n-cube really catches up with you. Okay, I'm going to quickly go over the second part of this, where I just want to pick your brains a little bit about what we plan on doing in the future, and so you guys can definitely help me out in terms of finding a good direction for this. Oh, this doesn't show up very well. This is roughly my research tree, and it's separated into 3 different categories. On the left-hand side, we have mostly more core graphics kind of problems. The middle side is more on visualization of urban forms, and the right-hand side is on a blend between architecture, specifically urban morphology, and what we've been working on so far. So I start with talking about the architecture and urban morphology. The idea here is that I just talked all this thing about urban legibility and how we use urban legibility for simplification. But the fact of the matter is, I never actually got back to saying, well, what are the legibility elements in a city? We have no idea where is the real road, where is a park, or anything like that. We just use the idea to do the simplification. Now, it'd be really cool if we can somehow go back and find out what are the elements. I mean, what are the important features to a city? So this we consider as kind of a feature extraction. And you can imagine that if we overlay a model using very, very strong simplification or a lot of simplification, we might end up with an image like this. And we overlay that on top of a map. Now we can start to see that here's a road, and on the GIS data set, it might say that that road is Main Avenue or whatever. And this area is something or other. Now we can start extracting really what are the elements that remain after our simplification. And we can do this, just pointing out some of the features here. And we can do this in an iterative manner where we start to do more and more simplification. And by doing that, more and more elements will start to appear. And eventually, you'll get all the way from the very, very important features down to the very, very fine-grained level of detail. And what that gets us is now we can have a ranking or a hierarchy of urban legibility elements, starting with the most important to the least important. And this allows us to be able to quantify and identify an urban model. And in other words, this allows us to actually have some semantic understanding of the model that we're looking at. And this is important because if we can start to do this, then we can start comparing between cities. So let's say, currently, if you ask any architects, are there any architects here? Okay, good. If you ask architects, what is the difference between New York City, Washington, D.C., and Charlotte? They would tell you that in a very abstract and a very subjective way that, oh, New York City is made up of a grid. Washington, D.C. is more of a ray-like structure where all the roads are emanating from the Congress and the White House. And then there's Charlotte that just has terrible urban planning, so the roads are just absolutely everywhere. But these are things that people can tell you in a very subjective way, right? But this is not quantifiable, this is not repeatable. And our goal is that if we can somehow start to quantify a city, then we can start really comparing between these different cities in a more objective manner. And along the same line, we can start to track how a city changes over time, again, in a quantifiable manner. Here I just showed 2 images. Again, this is Charlotte in 1919, and then this is Charlotte in today. This is roughly the same region, but you can see that a lot of expansion has occurred, and nobody can really tell you what, quantifiably speaking, what are the things that occurred over this 100 years. But what people can tell you is that in 1919, Charlotte is a pretty perfect grid. Oh, didn't show up very well. But in 1919, Charlotte is a very good grid. Our downtown area is, First Street, Second Street, Third Street, and so on. But once they start expanding, then the roads just go all over the place. Now, we presented this idea to a workshop, and we found out that this whole idea of being able to track the city changing over time is still a fundamental challenge in the GIS community. People have not had a good grasp on how to be able to do this in terms of a city changing over time. Along the same line, if we can start to quantify a city, the other thing that we'll be able to start doing is smart labeling, or in other words, position-based intelligent labeling. So for example, if I give you a model, again, this is of China, if somebody says, I'm here, and then ask about, well, what are the important things around me? Now we can start to say, well, here's a canal in front of you, here's E Street, this is Main Ave, and so on. Interesting thing that I want to point out is, now we can start to show the important features based on their relationship to where you are. So E Street, for example, might not be very important in a global sense of the word, or in the global sense, but locally to you, it might be very important. So we'll be able to highlight that because it's close to where you are. Similarly, Main Avenue, even though it's not related to you, but because it's important, we will show it. And then you can start to show greater regions such as downtown and just group all the elements within it into a district. The second half of this is more of an academic question. Now, if we can actually do the thing that we just said, can we reverse this process back to its beginning? In other words, can we start to sketch out a mental map similar to the ones that were drawn in Kevin Lynch's 1960 book? So we believe that there is a direct correlation between being able to do this point-based intelligent labeling and being able to retrieve a sketch of a mental map. So this will be a similar idea to what the Stanford group was doing with the intelligent route maps. But instead, we'll be doing mental maps instead. The second half of this research direction is on visualizing urban forms. And this is a very interesting problem for the architects, because they mentioned that the study of urban form really hasn't changed at all since the early 19th century. People today are still looking at urban forms as either 2D or 3D maps. So for example, this is something taken from ArcGIS, which is a product by Esri. And this is what people normally look at when the urban planner is looking at an urban model. Now, if you look at this, and even though you overlay additional layers of GIS information, in this case, you have some street information, you have some electricity information, the bottom line is these maps do not actively help the viewer understand changes or trends occur in the city. In other words, it really doesn't help an urban planner to be able to do his job any better. So what we like to do is to start to apply some things that we do know as visualization people. We want to apply some of these visual analytics techniques to urban form. So let's say that we start to integrate a lot of these more abstract visualization elements alongside this urban form idea. Now we can start to really see how a city changes just in a more data kind of perspective. And by the way, this is not actually built. The background image, this whole system was actually built for Bank of America on international wire transfer fraud detection. But it looks good together. So, and we showed this whole idea to the architects, and they immediately found things that they can start using. So, for example, the bottom image or the bottom window shows changes over time, and they can start to see how they can put in things that are changing in the urban model into such format. So we believe that this is very promising. And the last part is more of a graphics, core graphics kind of question. And this I'm definitely doing a lot of hand waving. There are a lot of people here who know a lot more about this than I do. But the first thing that we start realizing is using our method, we can really do some model compression. And on top of that, to be able to progressively stream the changes from coarse to fine. This is really well built into the system that we have, so this should be a very simple step. But I think it's an important step where not all the data has to be transferred all the time. You can just transfer incremental changes. And the second thing is we want to be able to extend this to 3D models. Now this is a much bigger problem because this includes true 3D models of buildings. And this also includes what we consider as trees and forests. Trees and forests is a very interesting topic in terms of GIS modeling and such, because people really haven't had a good grasp on this. Most people still do trees as billboards or a combination thereof. And realistically speaking, people haven't really done a great job in terms of seeing a whole lot of trees. So to us, the problem is very similar. On one side, we showed that we can do simplification of lots of very simple 3D, 2.5D urban models. And trees and forests are the same way. I mean, people have been able to do L system trees and whatnot, where you can procedurally generate trees. But viewing trees in a large quantity is still a very difficult problem. So we think that we might be able to use some of the ideas that we gained from doing 3D or 2.5D building models and apply it to trees and be able to take a stab at visualizing large quantity of trees, if not forests. So we took a quick stab at this, and what you're seeing here is basically a 3D model simplified using our method and eventually get back to the 3D convex hull. It's very preliminary, and the truth is going from 2D to 3D, there's a lot of technical difficulties that we haven't completely figured out yet, but we're taking some stabs at it, see where it goes. And that pretty much is the talk. Is there any questions? Comments? Yes, sir.
When you said the landmark detection in the first topic, you talked about tall buildings and so on. Have you tried that with actual data sets of the center of a city where most of the buildings are skyscrapers and they're all different heights?
Yeah, sorry, so the question is, in terms of landmark detection, have we done this in a scenario where all the buildings are skyscrapers? The answer is yes, and the idea there is that because the system doesn't really care about whether or not there's skyscrapers or not, the idea is you basically have a base cluster mesh. Anything taller than that, based on your current view position, would be shown on top of it or overlaying it. It doesn't really matter if they're all skyscrapers or not. They will still be rendered correctly in that sense. That's basically based on where your eye point is. Right. So that's a very good question, though. I can talk to you a little bit about this afterwards, but the idea of projecting your negative space, and the reason why the negative space is depicted as a 3D box is because you do want to know about the height. So when you're looking at a tall cluster mesh from the side, the projection of the negative space will still project to something really large, in which case it will be broken down into smaller sub-pieces. Okay. Anything else? Actually, just to follow up a little bit about that, there's some interesting question about what is considered as a landmark, and that's a very open question. You know, if you ask a person who lives in a city and you say, well, what is a landmark around where you live? They might pick out the local grocery store. You know, they might pick out the watering hole, the pub that you usually go to. Maybe because the pub has been there for 40 years and everybody knows about it. But from a purely graphics and visualization perspective, that information is not really as relevant because they're not visually important. But if we're trying to do this system for example, for the purpose of a mental map, then what constitutes as a landmark is not just purely geometry. Then you really have to start incorporating other GIS data sets to be able to figure some of those things out. Any questions? Any other questions? Well, thank you very much. I really appreciate it.